Welcome to this explainer, where we're going to decode the middle of the AI alphabet. Today, we're taking a dense glossary and turning it into a fast-paced, interconnected story about how artificial intelligence actually operates right now. We're going to cover a very specific, absolutely crucial sequence of the AI alphabet. We're talking G, H, I, J, K, L, M, N, O, P, Q, R, and jumping right to T. This sequence will give you a comprehensive picture of the tech that's driving our world today.
Because let's be real, it is so easy to get lost in the alphabet soup of AI buzzwords. But whether you're making tech investments, building new software, or just trying to keep up, you need to understand the architecture behind these terms. So let's cut through the jargon and master the nuances of this rapidly evolving space.
We are totally bypassing the basic ABCs today. I know you already know what an algorithm is. Instead, we're jumping straight into the deep end with the letters G through T. We'll find out exactly how AI is built, how it learns, and where it's headed next. By connecting these specific terms, we're going to map out the actual architecture of modern AI.
Let's kick things off with G, which stands for generative AI. This is the massive umbrella term for systems that create brand new content from the vast amounts of information they've already ingested. Unlike older AI that just categorized data or predicted a number, generative AI actually generates novel text, images, audio, and video right in response to your prompts. It's literally the engine behind the creative tech revolution we're living through right now.
Now let's see how this builds with GANs, that's Generative Adversarial Networks. This is a fascinating, highly specific type of generative AI. Imagine setting up a fierce competition just to force a machine to get smarter. In a GAN, you have two neural networks that essentially battle it out in a zero-sum game to learn and improve. It's basically artificial evolution through intense competition. The mechanics of that battle are so cool. On one side, you have the generator. Its whole job is to constantly create fake output, like an artificially generated face. Then, on the other side, you have the discriminator, which acts as a detective, trying to spot the fakes by comparing them to real-world data. As they compete, the generator gets unbelievably good at creating realistic data, which pushes both networks to become incredibly sophisticated. But here's the catch. Both of those networks, and really all AI models, are entirely dependent on their data quality, which brings us to another critical G term: garbage in, garbage out. It's a foundational rule of computer science. If you train your AI with flawed, mediocre, or low-quality data, the output will be exactly that. The machine can only ever be as good as the diet of data it consumes. And what happens when bad data or faulty logic takes over? We hit the letter H for hallucinations. This is when the AI confidently generates completely fabricated, false information without meaning to. It's crucial to distinguish this from a deepfake, by the way. A deepfake is an intentional manipulation. A hallucination is a genuine mistake by the AI, where it connects the wrong dots and presents a falsehood with absolute certainty. Fortunately, there's another H term, human in the loop, and this is exactly how we fix those shortcomings. We aren't just leaving the machines to run wild. Human in the loop is the practice of intentionally combining human intuition with machine intelligence. We actively intervene to train, tune, and test these algorithms, ensuring they don't hallucinate and that they operate accurately. Humans often help tune the letter I for image recognition. This is a massive subfield of computer vision where we guide the AI to correctly categorize visual features. By training the AI on millions of labeled images, it essentially learns to see. This tech is absolutely vital for industries like healthcare, identifying tumors in medical scans, or in automotive tech for self-driving cars. Oh, and before we move on, we can't forget the letter J for jailbreaking, which is the wild practice of testing these systems by actively trying to override the very safety protocols we just established. But assuming our parameters hold strong, we move straight to K. All these recognized facts and categorized data can feed into a knowledge-based system. Now, unlike a model that just guesses patterns, a KBS explicitly uses a vast digital library of domain knowledge and pairs it with an inference engine. It uses strict logic to reason through highly complex scenarios, a lot like how a human expert would diagnose a unique problem. All of these categorized facts beautifully transition us to the letter L. You hear about large language models, or LLMs, everywhere right now, but it's vital to understand that LLMs aren't magic. They're really just a massive text-based application of the broader machine learning field. They're just one specific tool in the broader AI toolbox. To define it properly, an LLM is an AI trained on astronomical amounts of text data. Because it has read millions of books, articles, and websites, it can understand, generate, and predict new content. It mimics human comprehension not by actually thinking, but by mathematically predicting what words should logically come next in a sentence based on the context you provide. Think about how this prediction process works in action. An LMM assigns mathematical probabilities to human language. If you give it the context, the human body, the model evaluates a whole vocabulary of potential next words. It guesses that the most likely next word is, followed by has, or maybe parts, based strictly on the statistical patterns it observed in its massive training corpus. It's essentially playing the world's most advanced game of fill in the blank. Zooming out quickly to M, all of this text prediction and image recognition and generative power is driven by machine learning. This is the core study of algorithms that can automatically learn from sample data. Instead of explicit human programming dictating every single rule, machine learning algorithms identify patterns on their own and improve their predictions with minimal human intervention. And where does that machine learning actually happen? It happens in N, neural networks. Inspired by the biological human brain, a neural network is a massive web of interconnected computational units, or nodes. Data passes between these units, activating different pathways, just like neurons firing in your brain, which allows the system to process incredibly complex inputs like speech and imagery. It's also worth noting that much of the neural network research driving today's tech landscape is completely open source. This means the underlying software and data are free to edit, share, and build upon. Open source is the absolute lifeblood of modern AI development. It allows a global community of researchers and developers to collaborate, share computing resources, and fix software bugs at an incredibly rapid pace. Looking objectively at P, we see both the malicious side of AI and its defensive capabilities with phishing. Phishing represents a cyber attack mechanism where bad actors impersonate trustworthy entities to steal information, often using AI to write highly convincing, personalized emails. But defensively, AI is increasingly deployed to analyze message context, sender behavior, and subtle anomalies to instantly block these impersonators before they ever reach your inbox. Looking ahead to the future of this tech, Q stands for quantum computers. Right now, training giant AI models takes weeks or even months using thousands of traditional computer chips. Quantum computers, running on the mind-bending principles of quantum mechanics, will soon process these massive AI algorithms exponentially faster. When quantum computing fully converges with machine learning, the leap in capabilities will be absolutely staggering. But before we get totally lost in the future, it's pretty fascinating to think this all started with R. Rossum's Universal Robots. This was a 1920 sci-fi play from a Czech writer that literally introduced the word robot to the English language. It told the story of an artificial race rising up against their creators. Over a century ago, art was already predicting the very technological revolution we're building today. Fast forward to today, skipping right to T. The most advanced systems rely heavily on transformers. Introduced in a landmark 2017 paper, a transformer is a breakthrough architecture that uses an attention mechanism. Instead of processing data word by word sequentially like older models did, transformers look at whole sequences at once. They shine a spotlight to weigh the importance of different pieces of information. This is the exact architecture that makes modern large language models possible. Which brings us to the ultimate historical benchmark for T, the Turing test. Proposed decades ago by computing pioneer Alan Turing, it was a simple thought experiment. If a machine's natural language conversation could completely fool a human evaluator into thinking it was a real person, it passed the test. For a long time, this was the absolute holy grail of artificial intelligence. But as we reflect on everything we've decoded today, from the competitive nature of GANs to the processing power of transformers and the sheer scale of large language models, I want to leave you with this final thought. With generative AI advancing this rapidly, how long until the Turing test is completely obsolete? We're entering an era where passing as a human is no longer the ultimate ceiling of AI, but just the baseline. Thank you so much for joining me on this explainer, and keep questioning what comes next.